Well, hello everyone. What we're going to look at today is a special class. This is truly virtual since when you hear and see this, I won't actually be in front of you. This is going to be a lesson that covers section 310, linear approximations and differentials. And I expect you to watch the video in full. And what's going to happen is I'm going to give you, as we go through this, 5 questions. And what you will do in the assignment, which will be called extra credit, is to do these questions and to write down the answers as best you can in text format into that assignment. And you have until Sunday midnight in which to complete that. So what's this topic, linear approximation and differentials, about? Well, if you can imagine a function, a nice normal no frills function like y equals f of x, and you choose a point on that curve there, and we'll assume that its x coordinate is a, then you can approximate this function by a straight line, as long as you don't travel too far away from a. So you can imagine, as long as you're in this range here, from here to here, then the value of that straight line and the value of the function will be very close to each other. And we call this line the linear approximation function. And it's typically written down as L of x, the linear approximation function. And its formula is f of a plus f dashed of a, x minus a. And if you're wondering, what does this function look like, or what is it? It's essentially the equation of the tangent line at x equals a. It just happens to be called the linear approximation function. And the reason why it's got that special name is that we're going to use this line, this equation of the line, to estimate the value of a function using a straight line approximation to what would be the origin. So I'll give you an example of how that works. Suppose I take a very simple curve, y equals x cubed, and I'm interested in the linear approximation at 1. So in other words, I would like to approximate the value of x cubed with a straight line, and I'd like to do it for values of x that are close to 1. So first thing I'm going to do is find its derivative. And then I'm going to find its derivative at 1. Which in this case will be 3. You can think of that as being the f of a, f dashed of a, I should say, the derivative at a. Well, I got my formula. My linear approximation function is therefore going to be the value of the function at a plus the value of the derivative of the function at a, x minus a. Now I know the value of this function at 1 is 1 cubed, so that's f of 1, which is 1 cubed. I know the derivative of the function at 1, which is this guy 3. And I know that x is 1, so a goes 1. And we're looking at that guy. Now, if you tidy up a little bit, what you get is 3x, negative 3 at 1, negative 2. And we now have our linear approximation function. Now let's take this function and see if we can use it to estimate the value of y equals x cubed to some number that's close to 1. We could, for instance, evaluate it perhaps at, I don't know, let's say 1.05. Now, the real value of the function is 1.05 cubed. So I'm going to calculate that just to see how good the approximation ends up being. And the correct answer, right, is 1.15765. Now, the linear approximation function is 3x take away 2. So I'm going to use this value of x and see what the linear approximation says it should look like. It should look like 3 of these guys take away 2. Well, I'll do that. And if you go 3 times 1.05, and then you subtract 2, the answer that I get is 1.15. Now, this here is the exact value. And this here is what the linear approximation function estimates it to be. And they're a pretty good match. I mean, if you look at the difference between them, which is essentially the error is quite small. The error is 0.007625. I think in lots of situations that well could be a pretty nice error. You'd probably be happy with that. So here is your first of your 5 questions that you need to do in order to get the 2% credit. So this is going to be called question 1. And in question 1, I want you to find the linear approximation to the square root of x, and I want you to do it at a equals 4. And that's going to be your question 1. And your question 2 is I want you to use your linear approximation function to estimate the value of the function at 4.4. Not only do I want you to estimate the value of the function like we did here, but I also want you to find out what the error is, just as we did here. And that's you, when you've done that, that's you've got 2 of the 5 questions that you need to get your extra credit. Put that there. Let's move on and look at another example of a linear approximation function. So I'm going to take a function, and I'm going to take sine x, and I'm going to do a linear approximation close to 0. So the derivative of this function is cosine of x, and the value of the derivative at a, which is 0, is the cosine of 0, which is 1. And the linear approximation function then is f of a plus f dashed of a, x take away a. And in this case, since a is going to be 0, it's the value of the function at 0, plus the derivative of the function at 0, x take away 0. The value of the function at 0 is the sine of 0, which is 0. The derivative at 0 is 1, and x essentially take away 0. So what we got in this case is that the linear approximation function is just x. So I should be able to estimate the value of sine x by just using the x value, as long as I keep really close to a equals 0. So I'm going to work on an estimate. Let's suppose I would like to estimate the sine of 0.1234566. And remember, this has to be in radians when you do it in your calculator. So if I go to my calculator and I'll just make sure I'm in radians, which I am. I should be able to get the exact value, or at least as close to exact as you can on a calculator, of 0.123456, and hit enter. And the answer I got is 0.1231426322. That's like overkill, really. Let's see what the linear approximation says the answer should be. 0.123, right? Because it's just the x value, 4, 5, 6. The error in this case, the difference between these two, is a remarkable 0.000, and I guess I could do a few more digits, maybe 3 and 1. I think if you could get an answer that was good to that tolerance, you'd be quite happy. So linear approximation function is essentially a way of taking any function, whether it's a trig function or a cubic or even a square root, and calculating a linear function that is approximately equal to it, close to whatever the a value happens to be. If you change that a value to some other number, this function will change accordingly, and therefore you have to make sure that you are choosing a value that's close to it. Otherwise, eventually it will end up miles away. Eventually, can you imagine a function that looked like this? And you have found a linear approximation, which is this line here, and this is a. Now, can you also imagine that as long as you stay pretty close to a, the error is basically the difference between the straight line and curve. It's pretty small there, but look what happens if you travel just a little bit too far away. If I try this guy here, can you see that the difference between what the straight line says as an estimate and what the curve is really equal to can be huge. And in fact, the further away from A you go, the more likely that is to happen. So we always bear in mind that you shouldn't travel too far away from the center value. In this case, A equals 0. So this now brings us to our next question. This is going to be question 3. And this question, I want you to find the linear approximation of y equals e to the x at a equals 0. That's it. Nothing else. Just calculate that. So while you're thinking about that particular situation, we will now move on to another linear approximation challenge. This time I'm going to make it a little bit harder. Let's have a function called g of x, and it's going to be the cube root of 1 plus x. And we're going to find a linear approximation at a equals 0. Well, I know I'm going to have to differentiate this guy. But to do that, I'm going to have to call it fractional power. I can then differentiate this guy. And you get 1/3, 1 plus x to the negative 2/3, which is going to be 1 over 3 lots of 1 plus x to the positive 2/3, which in turn, when I do the style points on it, is going to be the cube root of 1 plus x squared. Now the center value is a equals 0. So I know that I'm going to have to find the derivative at 0. But actually, it's not really a complicated thing because it's 3, essentially the cube root of 1 plus nothing squared, which is just 1. And the cube root of 1 is still 1. So what you get is that it's a third, so it's not that bad. So the linear approximation, which is the value of the function at a, plus the derivative at a, x minus a. This guy is going to be the value of the function at 0 again, the derivative at 0, x minus 0. Right, the value of this function at 0 you get from here. And this cube root of 1 is still 1. The derivative we found a minute ago is a third. And x minus 0 is x. So there is your linear approximation function. And you can use it to do things like, well, I'd like to estimate what the cube root of 0 0.3 is. Well, according to this, the cube root of 0.3 is 1 plus a third of 0.3, which is 1.1. And now I'm going to find the cube root of 0.3. And the answer I get is not good. It's 0.669. Now, can you see that there is a lot of error between here and here? So we would be a little bit unhappy, for want of a better word, about using this linear approximation, because even values that are reasonably close to 0 are phenomenally big. So some functions, some linear approximation functions, do a really good job, like the sine of x, and some do an extremely bad job. So you might think, well, why do some do a good job and others do a bad job? It's very often geometric. What do I mean by that? If you imagine a normal kind of curve, at certain points, like in this basic chunk of the world here, would you agree that the function is pretty linear? And so if I chose to do a linear approximation somewhere in that region, it would probably be pretty good. But if you chose a function, say, close to a hill, can you see that it doesn't take too long before the two start drifting apart really quickly? So things like the local max and mins and places like that tend to be bad places. Can you imagine you shouldn't try a linear approximation anywhere near a vertical asymptote? Also, don't try to find a vertical asymptote. Sorry, don't try and find a linear approximation function close to a vertical tangent line. Can you imagine how bad that would be? It wouldn't take too long to realize that that doesn't work well. So linear approximations are great, but they're not a panacea for every single situation. They work really well on most functions for most of their life, but there are some places it's better to avoid. Right? And what we're seeing here is an example of some place that is better to avoid. So what I'm now going to move on to is the second part of this topic. And that is differentials. There are essentially two differentials. They're called dy and dx. You might be familiar with those because we use that notation to represent a derivative. So dy is the top part, essentially, and dx is the bottom part. Now, there is a formula for calculating the relationship between the two. dy is f dashed of x dx. That is the differential formula. Now, what this tells us is that we can basically represent the difference in the y values as a multiple of the difference in the x values. So if you can visualize what that might mean for a function, y equals f of x. If I choose, say, this point here, if you do a basic tangent line, and you look at that particular guy, and we'll imagine this being called x. Then you choose another point from here to here, and this point here is going to be called x plus delta x. Now, that hits the straight line at this point, and it hits the curve a little bit higher than this point. So if I add an extra little horizontal line, then the distance from here to here is delta x, and the distance from here to here is delta y. So what we're looking at is, can you imagine that the ratio between these two is approximately the slope of the tangent line? Now, if you do a little cross multiply kind of thing, can you see that the difference in the y values is essentially this guy times dx? And if you imagine that if you made things approach each other so that the x and the x, and essentially if you made the delta x shrink to 0, you would get this relationship. So if you're wondering where the differential formula comes from, and that's not a formal proof, but you get the gist of how it's working. So the type of questions that you're going to get are to find the differential dy. And you're going to find it as a function of x, f dashed of x in this case, and a dx at the end. So suppose I give you a function like e to the 4x, and I asked you to find the differential dy. What you should do is you should find its derivative. I'm calling it f dashed of x. And hopefully you recognize this as a chain rule, e to the 4x times 4. Is that okay? So the differential dy, which is f dashed x dx, is 4e to the 4x dx. So you can think of dy as the difference between the real y value and the linear approximation y value. And dx as being the difference between x and this new point, because essentially delta x and dx are the same thing. They're equivalent. So the difference in the y values, right? If you imagine the difference between y and the other guy, dy, is given by this. So that is your differential. And another one. Suppose I wanted to find the differential of sine x. Then its derivative would be cosine x, and its differential would be cosine x dx. Try something a little bit more messy. Suppose I did the square root of t squared plus 1, and I'd like to know its differential. So I would need to call it t squared plus 1 to the power of half. If you differentiate this guy, you get a chain rule. So it's 1/2 t squared plus 1 to the negative a half times the derivative of t squared plus 1, which is 2t. If you tidy up these, you get t, and if you bring this downstairs, you get that. You can then convert this into something a little bit more respectable. So the differential dy is this fella, not dx now, but dt. So really, if you know how to differentiate a function, can't you get its differential? It's basically find the derivative, stick a dt in it, or find the derivative and stick a dx on it. So we now come to our fourth question. Let's have y equal to the natural log of x cubed plus x. And I want to find the differential dy. So, derivative is a chain rule, so it's 1 over x cubed plus x times the derivative of x cubed plus x, which I'm now going to call 3x squared plus 1 over x cubed plus x. So the differential will be the derivative dx. Now, if you've been watching this video, you will realize that this question 4 has already been done for you. So all you will need to do for this question 4 is to write your version of this. Now in text, it's going to be a little bit difficult. You're going to write dy, that's the easy part. Equals, that's pretty easy. You're going to have to do a bracket. 3x squared is going to be 3x, that funny little symbol, 2 plus 1, close the brackets. Divide symbol, start another bracket. X cubed plus x, close the brackets. Do a little bit of a space, dx. So that's what I will be looking for in this question. And you will be able to use this for your earlier questions, where you might not be able to exactly describe it as cleanly as you'd like, but that's the best we can do. We still have a little bit to do, and once that's done, this lesson will be over with. So I'm just looking at some possibilities here that we might want to do. So how about this one? Find the differential of e to the x over e to the x plus 1. Well, if I want to get its derivative, do you recognize, I hope, that what you're looking at is a quotient rule? And the top is e to the x and the bottom is e to the x plus 1. So you differentiate the top and you leave g alone. Take away, you leave the top and you differentiate the bottom. And you get e to the x plus 1 all squared. Now in this case here, you get e to the 2x plus an e to the x, take away an e to the 2x over e to the x plus 1 squared. They cancel, and you're now left with e to the x plus 1 squared. Now we're going to add an extra layer to this question. So if you like, can you think of this as being question A? Here's the function, find the differential dy. So what's question B going to look like? It's going to ask you to evaluate the differential dy, and it's going to tell you that x is going to be 0, and that dx is going to be 0.2. And the value of the differential then, because I just realized I haven't done it yet, is e to the x over e to the x plus 1 squared dx. And the value of the differential then is going to be that same guy, but when x is 0, oops, so dx there. So it's going to be e to the 0 over e to the 0 plus 1 squared times 0.2. And that's 1, and that's 1 plus 1, which is 2, and 1 plus 1 is 2, so that's 1 over 4. And 0.2 divided by 4 gives me 0.05. So if you're kind of wondering, what does this dy tell me? It's essentially a measurement of the error. It's telling me that the maximum error for using the function, this fella here, right, using a linear approximation at a equals 0, essentially that number, and only going plus or minus 0.2, essentially the dx. The maximum error that you get by using the linear function on this fella at 0, give or take 0.2, is that number. In other words, you're probably good to the first decimal place, but that's about it. Okay, let's try another one of that type of question. Suppose you're being asked to estimate e to the 0.02. And you can do it using a linear approximation technique. So what I'm going to look at this fella is what function I need to start with. Well, I think it's pretty clear that I should start with e to the x. And I need to have a center. Based on this number, it's very close to 0, so I'm going to do that fella. So what I can now essentially do is put these things together and get a linear approximation. So I've got this guy, his derivative is the same. The derivative at 0 is e to the 0, which is 1. The linear approximation function is f of a plus f dashed of a, x take away a. So it's going to be the value of the function at 0, the derivative at 0, x minus 0. The value of the function is e to the nothing, so that's 1. The derivative is e to the nothing, so that's 1. And what we got here is basically x plus 1. And we're going to use it to estimate this fella. Well, that would be 0.02. So that's going to be 0.02 plus 1, which is 1.02. I'm just curious how good that is. Well, if you do e to the power of 0.02, you get the answer 1.02020 and some stuff. Now that's pretty good. I mean, look at the difference. The error is 0.0002. We have got a pretty robust technique. Evidently, e to the x at 0 is a pretty nice function, right? plus 0.02 is pretty close to 0. And that combination has generated a linear approximation function that is very good at calculating the exact value of that. Our value, 1.02, compared to the real value, was very, very close to each other, right? The error was tiny. Okay, so our next and last question is I want you to estimate using linear approximation functions. Oops. I want you to estimate the square root of 9.3. Now they need to know two things here, so I'm going to be generous and tell you the two things that you need to know. You need to know what function would work with this, and I think I'm not giving anything away by saying it's the f of x, but you do need to choose an a value. And you don't just choose 0 because a lot of the questions choose 0. You have to choose a value that is going to be close to 9.3, but it also has to be a number that works well with square roots. And because of that, I'm going to be saying 9. So essentially, you are going to estimate the square root of 9.3 by finding its linear approximation function centered at a equals 9. And when you have got that answer, you are going to, again, type it into your assignment. And it's just going to be a number. So I'm pretending I know the answer. It's 3.1234. So that's all I will say for question 5. Now we're going to continue just a little bit further. There are a couple more questions that are in this, so I hope that you stay just because you want to know how to complete this homework exercise, because all these questions are similar to the ones that are in that exercise. And this lesson is going to replace a day where I would be doing this. So you really need to understand these last couple of questions just so you can complete the homework. So this one is like 13, and then I'll do the one after that's going to be like 14. Essentially what this question has is the radius of a circle is given as 26 centimeters. So we've got a circle and its radius is given as 26 centimeters. And the maximum error that you can get in this measurement is 0.2 centimeters. They've essentially told us that dx is 0.2. That's just the way that they phrase it. So this 26 might not be 26. It might be 25.8. It might be as big as 26.2. The dx is the variation, right? When you measure something, you never measure it exact in the real world, right? There's a bit of give or take. In this case, it's quite a big give or take. And question A is asking us to use differentials to estimate the maximum error, right, in its area. And we have to round off the answer to 2 decimal places. So essentially, A is going to be pi, I'll call it x squared, where x is the radius. So the derivative is going to be 2 pi x. So the differential, dA, is going to be 2 pi x dx. And this is going to be 2 pi. That's essentially the x value, so 26. And this is essentially the dx value. And put that package together, you get 2 times pi times 26 times 0.2. And the answer that we get here is 32 to, well, how many decimal places? 2 decimal places, so 32.67. And the units were centimeters, so since this is an area, it's 32.67. Now that means that if you imagine this circle, what's the maximum error that you could get? Well, if you can imagine a perfect circle that was 26, and then you had another circle which was 26.2, this circle would be bigger than that one. And that difference is essentially your error. And we're saying it's approximately 32.67. That's the most you could get as a difference between the perfect answer at 26 and what it might be if it was a little bit different from 26. Now they go on and they talk about 2 other kinds of error. And essentially that's the difference between what 26 and what the biggest error value would give. There are 2 other guys. One's called the relative error, and that's part B, and there's the other one that's called the percentage error. And these are very often calculated because they give you a little bit more insight into it. Now, the relative error is the error divided by the true value. And the percentage error is essentially the relative error written as a percentage. So I guess I need to know what the correct area is at 26, right, the true value, and compare it against the error. Well, I know what the error is. It's right, 32.67. Now, when you say, well, what do they mean by the true value? We are saying, if it was exactly 26, what would the true area be? So a circle with a radius of 26 would be pi times 26 squared. And that comes out to be 2123.716634. So the relative error here is 32.67 divided by the exact value, which is this fella. And the answer I get is 0.0154 because you want 4 decimal places. Now, what's the percentage error? 1.54%. So if you know that the circle has a radius of 26, but it could be give or take 0.2 centimeters, the error that you're going to get is about, at worst, about 1.5% over or under the true value. So you sometimes hear things like tolerance, right? You're allowed to be a couple of percent out kind of thing, then this would be safe. If you are not allowing that, if you say, look, the most I want to be is 0.5% out, then this wouldn't work, right? This is far too big an error. And that is us finished. Linear approximation functions and differentials. I hope that was enough for you to tackle your homework questions, and hopefully you've answered all 5 questions and put them into the Canvas. Now, when you go into Canvas, you'll see the thing, click on it. You've already done that because you've watched this movie, but you'll notice that below this movie, there's a text box where you actually type in your answers to questions 1, 2, 3, 4, and 5. And good luck, and I shall see you Monday.